once we've decided what our null hypothesis is and our alternative hypothesis and how many tails we're going to use, then we choose our level of significance. Now, this is an interesting question because there is no right answer, really. There are some not particularly good answers, and the usual answer is 0.05. Now, you may have heard that 42 is the answer to everything. Well, in statistics, 0.05 is pretty much the answer to things. It's often given as a thing called alpha, and it gives the level of evidence we need before we can claim that the null hypothesis isn't true. So say if we had used a 0.05 level of significance in rejecting the idea that there were 1/3 pinkies, the first time through we would have, after 3 pinkies, there was only a 0.03 of that happening, 0.04, so we would reject the null hypothesis after 3 pinkies and say we're pretty sure that it isn't 1/3 pinkies in the bag. Or in the second one, if I can ever find it, we would have waited until 8 before we could be sure that there's no pinkies in the bag. Okay. Why am I doing that? Yeah, don't worry about that, but just trying to think why it would be different. I'll come back to you on that one. Okay, so let's have a look. Oh, because we're looking at no pinkies. Sorry, the first one was that it was not 1/3 pinkies, and this is one before we can say... No, sorry, I've confused myself now. We'll go back to here. Okay, so 0.05 is the most popular choice, and that means we take a 5% risk of saying that something isn't true when in fact it is true, and that's called a type 1 error. And at the end of lecture 3 in this section, so that's next Thursday, we're going to do a whole lot more on types of error, which you're expected to know about. It means that if we chose instead 0.01, that would mean that we're pretty keen to hang on to the null hypothesis and will only accept strong evidence against it. 0.1 is sometimes used if you don't mind having a 10% chance. Now, can you think of some areas in life where it might be more important to get it right or wrong than in other areas? What about in diagnosing cancer? This is one they often use as examples. Okay, what would you rather do if you've actually got cancer and they say that and they say you don't? What chance do you want of them saying you haven't got cancer when in fact you have? Well, you probably don't want a very big chance of that. You'd like to have it down to say 0.0001 probably. You only want a 1 in 1,000 chance that they'll be wrong. And you're going, well, why can't they just say it anyway? Well, the only way they can be sure of being correct is by saying that everybody has cancer. And so you're always going to have this type 1 error. And the problem is that when you decrease your chance of a type 1 error, you increase your chance of a type 2 error. And this is the problem because then you get what are called false positives, is that people who are told they do have cancer when they don't. And this is one of the reasons why the pink ribbon guys are idiots, because they forced the mammogram age to be dropped to a level where the error rate is very high. I know it doesn't affect any of you because you're too young, but what it means is they've had hundreds and hundreds of false positives for breast cancer, which has clogged up the system, which meant that people who really do have breast cancer can't get the treatment they need. So sometimes what seems like an obviously good thing to do, if breast screening at 50 is good, then 45 must be better, is not actually the case because of the problem of false positives. So when we talk about this, if we reduce the likelihood of making a type 1 error, that's we miss something that really is there, we increase the probability of a type 2 error, which is that we say something's there when it isn't. So the thing about statistics that's so different from maths is that there generally aren't absolutes. There are right and wrong things that you can say, but you can never be 100% sure about most things in statistics.